Far beyond the planets, where the sun's light is just a faint glimmer, NASA's Voyager spacecraft made a startling discovery: a wall of plasma burning at 50,000 degrees Fahrenheit at the edge of our solar system. This mysterious barrier marks where the sun's influence ends and interstellar space begins. Scientists expected a smooth transition, but instead, Voyager found a turbulent frontier, a region pulsing with heat, energy, and charged particles. And if you want to uncover the full story behind this discovery, then watch this video till the end and subscribe to the channel. Let's begin. From that astonishing discovery, it's worth pausing to truly appreciate just how far Voyager has traveled to find it. Right now, Voyager 1 is more than 14 billion miles from Earth, so far away that a single radio signal traveling at the speed of light takes over 22 hours to reach it. That means when scientists send a command, it takes almost 2 days for a response to come back. Yet, despite the unimaginable distance and the fading power of its aging systems, Voyager still speaks to us. Its faint signal, weaker than the whisper of a snowflake hitting the ground, is captured by the giant dishes of NASA's Deep Space Network, decoded and transformed into precious data. Each transmission carries the story of what lies beyond the sun's protective bubble, revealing a realm that no human eye has ever seen. It's incredible to think that a spacecraft launched in the 1970s, built with technology less advanced than a modern smartphone, continues to operate in the frozen darkness of interstellar space, faithfully sending messages home from the edge of forever. Voyager's journey into the unknown didn't begin as a mission to touch the stars. It started as a bold plan to explore our own solar system. In 1977, NASA launched 2 identical spacecraft, Voyager 1 and Voyager 2, during a rare alignment of the outer planets that happens only once every 176 years. This alignment allowed the probes to use each planet's gravity as a slingshot to propel them to the next, saving both time and fuel. Their original mission was to visit the gas giants, Jupiter and Saturn, and study their moons, rings, and magnetic fields in unprecedented detail. Voyager 2 would later continue even further, becoming the first and only spacecraft to visit Uranus and Neptune, completing the grand tour of the outer solar system. But after their planetary encounters ended, something remarkable happened. Both Voyagers just kept going. Their trajectories carried them beyond the orbit of the last planet, toward the edge of the sun's influence. Over the decades, they transformed from planetary explorers into interstellar pioneers, becoming humanity's most distant emissaries. Each carries a golden record, a time capsule of sounds and images from Earth, greetings in multiple languages, music from across cultures, and even the laughter of children, a hopeful message to any intelligent beings that might someday find them. Long after Earth itself is gone, the Voyagers will still drift silently through the stars, carrying our story with them. As Voyager continued its outward journey, leaving the familiar planets far behind, it eventually reached a region that scientists often refer to as the edge of the solar system. But what exactly does that mean? It's not as simple as crossing a line on a map or passing Pluto's orbit. The true edge of our solar system isn't defined by where the planets end. It's defined by where the sun's influence fades. That invisible frontier lies in a vast, dynamic region known as the heliosphere, a gigantic bubble carved into space by the sun itself. This bubble is filled with the solar wind, a stream of charged particles and magnetic fields continuously flowing outward from the sun in all directions, traveling at millions of miles per hour. For billions of miles, this solar wind dominates the space around us, pushing back the thin gas, dust, and radiation that fill the rest of the galaxy. As long as the solar wind is strong enough, it creates a sort of cosmic shield around everything we know. Every planet, moon, and comet, protecting them from the harsher environment of interstellar space. But this protective bubble doesn't go on forever. Eventually, far beyond Pluto, the solar wind begins to lose strength as it collides with the interstellar medium, the diffuse gas and plasma that fill the space between stars. When the pressure of the solar wind finally equals the pressure of this external interstellar gas, the boundary of the Sun's domain is reached. This boundary is called the heliopause, and it represents the true edge of the solar system. The heliopause isn't a fixed wall though. It breathes and shifts like a living membrane, expanding and contracting as the Sun's activity changes over its 11-year solar cycle. When the Sun becomes more active, spewing out intense solar storms and flares, the heliosphere swells outward, pushing the boundary a bit farther into interstellar space. When the Sun quiets down, the bubble shrinks back in. In this way, the shape of our solar system's frontier is always changing, invisible yet alive with motion. Voyager 1's mission took it directly through this boundary, allowing humanity to measure it for the very first time. Scientists had long theorized what might happen there, that the solar wind would slow down, the magnetic field would become distorted, and the density of particles from interstellar space would increase. Yet, as Voyager approached this region, its instruments began detecting something far stranger and more complex than any model had predicted. Instead of a gentle transition, there was turbulence, heat, and unexpected bursts of plasma activity. A region far more chaotic and energetic than anticipated. What makes the heliopause so fascinating is that it represents not just a physical limit, but a kind of cosmic frontier. The place where our Sun's influence ends and the galaxy begins. Everything within it is part of our solar system, shaped by the energy and magnetism of our star. Everything beyond it belongs to the Milky Way, an endless ocean of interstellar space filled with ancient dust, cosmic rays, and mysterious forces that have existed since long before our Sun was born. For Voyager, crossing this boundary was more than just a milestone in distance. It was a crossing into the unknown. It marked the first time in human history that a spacecraft left the bubble of our Sun's protection and entered the interstellar medium directly. To think that something built by human hands, launched before personal computers even existed, has now passed beyond the heliopause is both humbling and awe-inspiring. Voyager didn't just define where the solar system ends, it revealed how vast and complex that edge truly is. The discovery of this frontier, and the intense, hot plasma wall that lurks there, has reshaped our understanding of how the Sun interacts with the galaxy around it. What once seemed like a quiet, empty border has turned out to be a turbulent, energetic boundary where two vast cosmic forces collide. The heliopause is more than a dividing line. It's a place of transformation, a zone where solar and interstellar matter clash, mix, and give rise to phenomena we're only beginning to comprehend. And as Voyager transmitted those first measurements back to Earth, scientists realized that what lay ahead was even more intriguing. To truly grasp what this strange region was made of, they'd have to understand the nature of the heliosphere itself, the enormous bubble that surrounds our solar system and shields everything within it from the cold, harsh forces beyond. The story of Voyager's journey beyond the solar system's edge cannot be understood without first understanding the vast, invisible force field that protects everything we know, the heliosphere. Picture it as a colossal, teardrop-shaped bubble surrounding our solar system, stretching for billions of miles in every direction. It's not made of solid material, but of plasma, magnetic fields, and the ever-flowing solar wind, the constant outpouring of charged particles from our Sun. Every second, the Sun ejects streams of protons, electrons, and atomic nuclei that race outward at nearly 1 million miles per hour. This relentless wind sculpts the space around us, sweeping away interstellar dust and forming a gigantic, dynamic cocoon that shields our planets from the harshest radiation of the galaxy. At its core, the heliosphere is shaped by the Sun's magnetic field. As the Sun rotates, its magnetic field twists and spirals outward, carried by the solar wind in a vast structure known as the Parker spiral. This ever-turning magnetic web creates a force field that influences everything within it, guiding charged particles, deflecting cosmic rays, and helping to maintain the delicate balance that allows life to thrive on Earth. Without the heliosphere, our planet would be bombarded by a far greater dose of high-energy cosmic radiation, which could erode our atmosphere and damage living cells. In many ways, the heliosphere acts as the solar system's first line of defense, a protective shield shaped by the breath of our star. But this cosmic bubble is far from static. It expands and contracts in rhythm with the Sun's activity. During periods of intense solar storms, when massive bursts of plasma called coronal mass ejections erupt from the Sun's surface, the solar wind becomes denser and more forceful, pushing the heliosphere outward into interstellar space. During quieter times, when the Sun's surface calms, the bubble relaxes and shrinks slightly inward. This constant pulsation creates a boundary that breathes, a living border between the domain of our Sun and the vastness beyond. To get a sense of its scale, imagine this. The heliosphere extends far beyond the orbit of Pluto. In fact, if the Sun were at the center of a city, the Earth would be just a single block away, while the edge of the heliosphere would lie nearly 50 miles out. Voyager 1 and 2, traveling in opposite directions, took more than 40 years to reach that frontier. It is so immense that light itself, the fastest thing in the universe, would take over 16 hours to cross from one side to the other. This gives us an appreciation of just how enormous our Sun's influence truly is, even at distances where its light is only a faint glimmer. Inside this immense bubble, the solar wind reigns supreme, but at its limits, the pressure from interstellar space begins to push back. Scientists call this region the heliosheath, a turbulent zone where the solar wind slows and piles up as it meets the opposing flow of interstellar plasma. This is the outermost layer of the heliosphere, a place of collisions, compression, and heat, and it's here, just before the boundary of the heliopause, that Voyager detected the strange wall of 50,000-degree plasma. What Voyager found in this region revealed that the Sun's influence doesn't end abruptly, but rather bleeds into interstellar space in a complex dance of energy and matter. The shape of the heliosphere is also fascinating. It's not perfectly spherical. Because the solar system moves through the galaxy at high speed, about 450,000 miles per hour, the heliosphere is compressed at the front and stretched out behind, much like the tail of a comet. The side facing the direction of our motion forms a kind of bow wave, where the solar wind and the interstellar medium meet head-on. The trailing side, meanwhile, stretches into an elongated tail called the heliotail, which may extend for hundreds of billions of miles. Voyager 1 is traveling toward the front of the heliosphere, while Voyager 2 took a path toward its flank, giving us a three-dimensional glimpse of this immense structure for the first time. Understanding the heliosphere isn't just about knowing where our solar system ends. It's about understanding how our Sun interacts with the galaxy. Every star has its own version of a heliosphere, known more generally as an astrosphere, and by studying ours, we gain insight into how other stars carve out their own safe havens in the cosmos. The heliosphere protects us from about 75% of the harmful galactic cosmic rays that would otherwise bombard Earth. Without it, life as we know it might never have emerged. Voyager's crossing of this vast shield is not just a journey through space, it's a journey through the limits of our star's reach. As it moved outward, Its instruments detected the gradual weakening of the solar wind, the rise in external particle pressure, and the faint signals of the interstellar environment pressing against the Sun's outermost boundary. The spacecraft's readings helped confirm that the heliosphere is a living structure, molded by both internal solar forces and the external pressure of the galaxy around us. And just beyond that boundary, beyond the Sun's protective bubble, lies a region so different, so alien, that even our most advanced models struggled to predict what Voyager would find. That realm is called the interstellar medium, the vast expanse of cold, diffuse matter that fills the space between stars. And it would soon become the next great chapter in Voyager's extraordinary story. Beyond the Sun's protective cocoon, past the turbulent edges of the heliosphere, lies a realm that, for most of human history, existed only in theory: the interstellar medium. It is the space between the stars, a place that sounds empty, but is, in fact, subtly alive. Voyager, now venturing into this great cosmic ocean, has given us our first direct glimpse into what it's truly made of. Out here, there are no planets, no solar winds, no magnetic comfort from a nearby star. The interstellar medium is vast, ancient, and hauntingly still, a silent expanse of thin gas, dust, magnetic fields, and cosmic rays that weave through the Milky Way like invisible threads of creation. To understand how alien this region is, consider the emptiness itself. In a cubic centimetre of interstellar space, there might be one lone atom, mostly hydrogen, occasionally helium, and traces of heavier elements formed in the hearts of long-dead stars. By contrast, that same space near Earth's orbit contains millions of particles. The interstellar medium is so thin that it would seem like a perfect vacuum to us, yet it's far from lifeless. It is the recycling ground of the galaxy, a place where material from dying stars, cast off in supernova explosions or stellar winds, drifts through space until it clumps together again to form new stars, new planets, and new worlds. Every atom of carbon, oxygen, and iron in our bodies once drifted through this same cosmic sea. What makes the interstellar medium especially intriguing is that it's not uniform. It's a patchwork of regions with different temperatures, densities, and magnetic pressures. Some zones are cold and dense, where gas begins to collapse into new star-forming clouds. Others are hot and ionized, blasted by radiation from massive stars or shockwaves from supernovae. Between these extremes lies a kind of galactic weather, flows and eddies of particles moving under the influence of magnetic fields, light pressure, and gravity. These slow, invisible currents shape the evolution of galaxies and the life cycles of stars themselves. When Voyager crossed into this interstellar expanse, it left behind the warmth and magnetism of the Sun's domain and entered a place defined by entirely different forces. Its instruments began detecting a marked increase in plasma density, confirming it had passed into a region where the solar wind no longer dominated. Yet, curiously, it also found that the magnetic field's orientation hadn't changed as much as scientists expected. This suggested a complex layering between the heliosphere and the interstellar medium. Not a clean break, but a turbulent boundary where solar and galactic forces intertwine. The interstellar medium is also filled with cosmic rays, high-energy particles that travel near the speed of light and can penetrate almost anything. Within the heliosphere, the Sun's magnetic field deflects many of them, but out here, unshielded and raw, Voyager is bathed in a constant flux of these ancient travelers. They are relics from supernovae, violent stellar deaths that scatter energetic particles across the galaxy. Each cosmic ray carries clues about distant astrophysical events, and as Voyager measures their intensity, scientists can map
how the sun's magnetic bubble filters and modulates them. Temperature in this region becomes a strange concept.
Space out here is incredibly cold, just a few degrees above absolute zero.
Yet the few atoms that do exist can carry enormous energy, making them technically hot in terms of kinetic motion. It's a paradox of cosmic physics, near perfect emptiness, where the rare particles that exist move so fast they reach temperatures of tens of thousands of degrees. This is part of what makes the 50,000-degree wall Voyager encountered so fascinating. The transition between two extremes, between the sun's fading breath and the chill of the interstellar abyss. The interstellar medium also holds the faint glow of the galaxy's history. It's suffused with radiation from countless stars, as well as the distant whisper of the cosmic microwave background, the afterglow of the Big Bang itself. Voyager's instruments, though not designed for this kind of exploration, can sense subtle shifts in this radiation, giving us an indirect look at how our solar system interacts with its galactic environment. Every signal it sends home helps scientists refine their understanding of how energy and matter move through the Milky Way, how stars are born, how they die, and how their remains seed the next generation of worlds. Voyager's arrival in the interstellar medium was more than just a technical milestone. It was a philosophical moment. For the first time in history, a human-made object left the cradle of our sun and touched the galaxy itself. It's as though a single grain of sand from a beach had floated beyond the shoreline and begun to drift into the open ocean.
The space beyond the heliosphere is our galaxy's true frontier, vast, perilous, and filled with mysteries we are only beginning to sense. And as Voyager pushed deeper into this quiet realm, its instruments began to pick up something astonishing, a strange, sudden rise in temperature and density, signaling that it had crossed into a region unlike anything encountered before. This wasn't just the cold calm of interstellar space. It was a transition zone, a fiery barricade of plasma marking the last gasp of the sun's influence. Scientists soon realized they were seeing the impossible, a 50,000-degree wall at the edge of the solar system. As Voyager drifted ever closer to the sun's frontier, scientists back on Earth braced for a quiet crossing, a gradual, almost undetectable shift from the solar wind's fading breath into the stillness of interstellar space. But when the data finally arrived, it told a very different story. The edge of the solar system was not calm. It was alive, violent, and hot. A turbulent transition unlike anything ever recorded before. Voyager's instruments began picking up strange signals. The spacecraft, traveling through the outermost layer of the heliosphere, the Helios Heath, started to detect a sudden spike in charged particle density. It was as though it had entered a region where particles were crowding together, compressed by some invisible pressure. At the same time, its plasma wave sensor registered an unexpected surge in energy, a tone so distinct that scientists recognized it immediately. The faint, oscillating sound of particles vibrating at incredibly high frequencies. These vibrations were the telltale signature of superheated plasma, and as the readings were analyzed, the numbers stunned researchers. The plasma temperature had soared to nearly 50,000 degrees Fahrenheit, tens of thousands of degrees hotter than models had ever predicted for this region. For decades, scientists had imagined the boundary between the solar system and interstellar space as a smooth gradient, a place where the sun's wind gently faded into the galactic background. But Voyager's data revealed something far more dramatic. It had encountered what could only be described as a wall, a zone of compressed, superheated plasma where the solar wind and the interstellar medium collided head-on. The density of particles had risen by more than 40 times what it was just a short distance inside the heliosphere. This wasn't a gradual fade. It was a collision front, a boundary
where the forces of our Sun met the pressures of the galaxy in a fiery standoff. The first clues came in 2012, when Voyager 1 crossed what scientists then believed to be the heliopause, the outer edge of the heliosphere. Its instruments, though partially degraded after decades in space, detected a sharp rise in the number of cosmic rays from interstellar space and an equally sharp drop in solar particles. That was the expected sign of crossing the solar boundary. But then something odd happened. Instead of entering a region of calm, Voyager found itself in a stormy plasma environment where the temperature and density fluctuated wildly. Even stranger, the magnetic field's direction, which was supposed to shift dramatically once outside the Sun's influence, stayed almost the same. This inconsistency left scientists puzzled. Had Voyager truly left the heliosphere, or was it still inside a strange outer layer no one had predicted? Over the following months, more data trickled in. Faint, delayed radio signals that took nearly a day to reach Earth. They painted a clearer picture of what Voyager was passing through, a compressed barrier of trapped solar particles that had been slowed and heated by their collision with interstellar plasma. The spacecraft's detectors picked up pulses, plasma oscillations, created by shockwaves from solar storms that had traveled all the way from the inner solar system. When these shockwaves reached the boundary, they slammed into the denser plasma, setting it vibrating like the surface of a drum. By measuring the frequency of those vibrations, scientists could determine the plasma's density, and it was far higher than anything seen before. This was the moment they realized Voyager had found something extraordinary. The readings showed that the spacecraft had entered a transition zone, a liminal region neither fully solar nor fully interstellar. It was a place of turbulence and compression, where charged particles piled up and heated under pressure, forming what could only be described as a wall of fire. The discovery sent ripples through the scientific community because it suggested that the edge of our solar system wasn't just a fading boundary. It was a dynamic, reactive interface, constantly reshaped by solar activity and galactic forces. Adding to the tension was the fact that Voyager was running on borrowed time. Its nuclear power source had been slowly degrading for decades. Every bit of data it sent could have been its last. Engineers at NASA's Jet Propulsion Laboratory carefully managed its systems, shutting down non-essential instruments to preserve power for the most critical sensors. Each transmission was an act of endurance, each reading a precious glimpse into the unknown. When the plasma wave data confirming the 50,000-degree temperature finally arrived, it was as if Voyager had called back across the abyss to say, "There's something here, and it's far stranger than we imagined." This boundary, this burning wall at the solar system's edge, wasn't just a discovery of physics. It was a reminder of how unpredictable the cosmos remains. Voyager had traveled through the planetary realms where gravity and sunlight ruled, through the cold, empty outskirts where darkness reigned. And now it had entered a frontier of energy and resistance, a place where the forces of our Sun and the galaxy collided in a slow, cosmic struggle. No human had ever been here. No spacecraft had ever crossed this threshold before. And in that moment, as the data streamed back across billions of miles, humanity caught its first direct glimpse of what truly lies at the border between our home star's influence and the endless, untamed ocean of the Milky Way beyond. When scientists refer to Voyager's discovery as a plasma wall, they aren't describing a solid barrier or a visible structure like a glowing curtain of light. Instead, they're talking about a region of intense energy and charged particles, a turbulent zone where the solar wind, racing outward from the Sun, collides with the interstellar medium pushing back from the other side. It's here, in this thin but powerful boundary, that matter, magnetism, and motion all reach a boiling point. To Voyager's senses, this wasn't just another part of space. It was a fiery compression zone, a cosmic traffic jam where particles slowed, accumulated, and heated to astonishing levels.
The wall is made of plasma, which is not a gas, liquid, or solid, but the fourth state of matter, a soup of electrons and ions stripped of their atoms. Plasma dominates most of the universe, from the interiors of stars to the diffuse material between galaxies. In this case, the plasma wall exists because the solar wind, a stream of hot, magnetized particles emitted by the sun, eventually encounters the pressure of the interstellar plasma, which flows from the galaxy itself. As these two forces meet, neither gives way easily. The solar wind can no longer flow freely outward, and the interstellar medium can't flow easily inward. The result is a narrow, high-energy boundary where charged particles pile up, slow down, and become superheated, like air compressing and igniting at the edge of a shockwave. This wall wasn't expected to be so energetic. For years, scientists thought the solar wind would gradually lose speed and temperature until it simply blended with the interstellar environment. But Voyager showed otherwise. As it crossed this zone, its plasma wave instrument detected that the density of charged particles had jumped nearly 40-fold, while their temperature skyrocketed to about 50,000 degrees Fahrenheit. In a sense, it's the cosmic equivalent of a dam. The sun's outward flow of particles meets the galaxy's inward pressure, and everything caught in between heats up as the energy builds. The reason it's called a plasma wall rather than a simple boundary is because it behaves more like a dynamic shield than a static barrier. The region shifts and ripples in response to changes in solar activity. When massive solar storms erupt, shockwaves of plasma travel outward for months or even years until they reach this outer frontier. When those shockwaves slam into the compressed boundary, they momentarily superheat it, creating bursts of energy that ripple across billions of miles of space. Voyager's instruments have detected several of these events. Sudden rises in plasma oscillations that confirm this wall isn't stable but alive, constantly stirred by the heartbeat of the sun. Interestingly, the plasma wall also appears to trap particles from both sides. Some of the solar wind particles get stuck there, caught in the tangled magnetic fields that weave through the region. Meanwhile, high-energy cosmic rays from interstellar space are partially deflected or slowed as they approach it. This means the wall acts like a kind of filter, determining how much galactic radiation reaches the inner solar system. In that sense, it's a critical component of our sun's defense system, a natural shield protecting everything within, from the smallest comet to the Earth itself. Magnetically, this boundary is just as fascinating. Voyager's magnetometer detected that as it approached the wall, the strength of the magnetic field increased significantly, suggesting that the sun's magnetic influence doesn't simply stop at the heliopause, but gets compressed and intensified before giving way to interstellar fields. Imagine two vast magnetic bubbles, the suns and the galaxies, pressing against each other. The region where they meet is full of twisting, tangled field lines, where energy builds up and occasionally releases in bursts, much like miniature solar flares on a galactic scale. The term wall might sound like something impenetrable, but Voyager, tiny and determined, passed through it. The spacecraft moved at about 38,000 miles per hour, slow by cosmic standards, but steady enough to cross this turbulent zone over several months. During that time, it recorded data that continues to challenge our understanding of how the sun's influence ends. The plasma wall is not a neat boundary. It's more like a cosmic storm front, an area of chaos and transformation where the sun's power fades but does not yet vanish. To visualize it, think of the heliosphere as a ship sailing through the galactic ocean. Around it, the solar wind creates a wake, a bubble of protection moving through the cosmic sea. But at the very front of the ship, where the hull meets the waves, the water piles up, churns, and foams violently. That frothing, turbulent edge
is the plasma wall. It's where the forces of motion and resistance meet, where the sun's outward energy and the galaxy's inward pressure find equilibrium through chaos. Voyager's data showed that this wall isn't just a thin line, but a layer hundreds of millions of miles thick, filled with compressed plasma and magnetic tension. It marks the final stand of the sun's influence, where the solar wind's last remnants are transformed by their struggle with the interstellar environment. On one side lies everything we know: the planets, the sun, the familiar warmth of our cosmic home. On the other side lies the cold, uncharted void of the galaxy. And between them burns this mysterious, unseen barricade, glowing with energy we can only measure indirectly. That's the plasma wall, not a wall of matter, but a wall of force, an invisible furnace forged by the meeting of two vast cosmic domains. Voyager's discovery of it revealed that the solar system doesn't end quietly. It ends with fire, with friction, and with a final, defiant blaze of energy marking our passage into the interstellar deep. When scientists say that Voyager found a region of plasma reaching 50,000 degrees Fahrenheit at the edge of the solar system, it's easy to picture a wall of fire, something blazing and unbearable, like the surface of a star. But in truth, the term 50,000 degrees means something very different in space than it does on Earth. It doesn't describe heat in the way we feel it. There are no flames, no glowing embers, no warmth at all. Instead, it describes the kinetic energy of charged particles, how fast they're moving, how much they're colliding, and how much energy each one carries as it zips through space. Out in the heliopause region, where Voyager made its discovery, matter is almost non-existent. The plasma there is so tenuous that even in a space the size of your living room, there might be only a handful of particles. A few stray protons, electrons, and ions scattered across immense distances. Because there are so few of them, they almost never collide with one another. On Earth, heat is something we feel because molecules in the air are constantly bumping into our skin, transferring energy. But in the vacuum of interstellar space, that kind of transfer doesn't happen. Even if each of those particles is moving at enormous speeds, the equivalent of tens of thousands of degrees, there just aren't enough of them to make you feel any warmth. You could drift through this 50,000 degree plasma and feel nothing but the cold emptiness of space. So when scientists talk about temperature in this context, they're referring to particle velocity, how much energy those particles have, not the sensation of heat. The temperature is calculated from the average kinetic energy of the ions and electrons that make up the plasma. A hotter plasma means that, on average, the particles are moving faster or vibrating with greater intensity. In the heliosheath, where the solar wind slows down and collides with the interstellar medium, the energy of these collisions increases dramatically. That's why the plasma temperature spikes so high. It's not because the space suddenly fills with more heat. It's because the few particles that are there are moving with incredible energy. Another way to think about it is like this. Imagine standing in a room filled with 1 million slow-moving tennis balls. You'd feel constant impacts, like heat on your skin. That's what happens on Earth, where air molecules constantly collide with us. Now imagine being in a vast arena with only a handful of tennis balls, but each one is fired at you by a cannon at thousands of miles per hour. There are far fewer impacts, but each one carries far more energy. That's what's happening in the plasma wall. The density of particles is minuscule, but their speeds, and therefore their energies, are enormous. Voyager's instruments were able to detect these energetic particles through their plasma wave system, which measures oscillations in the charged particles around the spacecraft. When plasma is heated or compressed, it vibrates in predictable ways. By analyzing the frequency and intensity of these vibrations, scientists can determine the density and the energy level of the plasma. From this,
they infer the temperature, a number that captures how energetically the particles are behaving, even if there's no heat in the traditional sense. The 50,000 degree reading shocked scientists because it was far hotter than any existing model had predicted for the heliopause region. Earlier theories suggested that as the solar wind slowed and cooled while pushing against the interstellar medium, its temperature would fall to a few thousand degrees at most. Instead, Voyager found that the plasma was being compressed and energized, raising the particle speeds to levels equivalent to 50,000 degrees. It was as though the solar system's boundary had turned into a furnace, not one that radiates light or warmth, but one that thrums with invisible kinetic fire. It's also important to note that different particles in this plasma don't share energy equally. The lighter electrons move faster and respond more quickly to magnetic fluctuations, while the heavier ions move more slowly but carry the bulk of the plasma's mass. These differences create a kind of internal turbulence, a microscopic storm of swirling charged particles that contributes to the heating process. The result is a zone of chaotic motion, where magnetic energy and particle motion continuously exchange power, sustaining the plasma's intense temperature. To further put this in perspective, consider the surface of the Sun, which burns at around 10,000 degrees Fahrenheit. By comparison, the plasma at the edge of the solar system is 5 times hotter in terms of particle energy, yet completely dark, invisible, and almost empty. This paradox of extreme energy in near-empty space is one of the most fascinating aspects of plasma physics. The heliopause region shows us that temperature in the cosmos isn't just about how hot something feels, but about how fast energy is moving through even the most rarefied of materials. In essence, the 50,000 degree wall is not a place of heat, but a place of motion and collision, where the sun's dying breath meets the galaxy's quiet resistance. It's a reminder that even in the coldest reaches of space, energy is never gone, only transformed, hidden in the ceaseless dance of charged particles moving faster than we can imagine. And through Voyager's tiny instruments, humming quietly in the dark, over 14 billion miles from home, we caught the first glimpse of that dance at the very edge of the Sun's domain. Voyager's ability to detect the 50,000 degree plasma wall, and, in fact, to tell us anything at all about the environment beyond the Sun's reach, is a testament to the extraordinary engineering and foresight of the people who built it nearly half a century ago. Remember, Voyager 1 and 2 were launched in 1977, long before modern computers, long before digital data recorders, and decades before anyone even imagined a spacecraft crossing into interstellar space. Yet, through a clever combination of analog instruments and careful scientific design, these two probes can still sense and transmit the faintest whispers of the cosmos, including the properties of plasma, magnetic fields, and cosmic rays. To understand how Voyager measured the wall of hot plasma, we have to look at a few key instruments that make up its interstellar mission payload. The most crucial among them is the Plasma Wave Subsystem, PWS, essentially Voyager's ears. This instrument listens for the high-pitched vibrations produced when charged particles in plasma oscillate. You can think of it like a cosmic stethoscope tuned to the frequencies of interstellar matter. When a solar storm or shockwave passes through a region, it sets nearby electrons vibrating. Those vibrations travel as plasma waves, and the PWS records their frequency and amplitude. By analyzing those signals, scientists can determine how dense the plasma is, because denser plasma vibrates at higher frequencies. In 2012, when Voyager 1 crossed the heliopause, it began to detect these plasma oscillations with astonishing clarity. The frequencies indicated that the plasma density outside the heliosphere was about 40 times higher than the density inside, confirming that Voyager had entered the interstellar medium. Later readings in 2020 showed similar vibrations, caused by distant solar storms that took nearly a year to travel the 14 billion miles to Voyager's location. By measuring the interval between these waves, scientists could infer not only the density but also the temperature and pressure of the plasma, leading to the discovery of that 50,000-degree region of compressed, energetic particles. But the plasma wave data alone wasn't enough to tell the full story. Voyager also carried a magnetometer, MAG, a long, sensitive boom-mounted device that measures the strength and direction of magnetic fields around the spacecraft. The magnetometer revealed that as Voyager approached and crossed the heliopause, the magnetic field intensity increased sharply, another clear sign of compression at the solar boundary. However, one surprise came when the field's direction barely changed after the crossing. This meant that the solar magnetic field and the interstellar magnetic field might be partially connected or twisted together at the boundary, rather than neatly separated as scientists had once believed. The result was a picture of a turbulent, tangled interface rather than a clean divide. Another essential tool was the Cosmic Ray Subsystem, CRS. This instrument was designed to detect high-energy particles, the cosmic rays that stream through the galaxy and occasionally penetrate the heliosphere. Inside the Sun's magnetic bubble, cosmic rays are partially blocked by solar wind and magnetic turbulence, meaning their intensity is relatively low. But once Voyager crossed the heliopause, the CRS recorded a sudden and dramatic increase in cosmic ray intensity. That spike was one of the first definitive signs that the spacecraft had entered interstellar space. These cosmic rays, moving near the speed of light, carry the fingerprints of distant supernova and galactic events. By studying their energy and distribution, scientists can infer how much shielding the heliosphere provides, and how that shielding breaks down at the boundary. The fourth piece of the puzzle was the low-energy charged particle, LECP detector, which measures slower-moving ions and electrons emitted by the Sun. Inside the heliosphere, these solar particles are plentiful. As Voyager moved outward, scientists watched their numbers drop sharply, almost disappearing when the spacecraft crossed into the interstellar region. This depletion, combined with the cosmic ray increase and the plasma wave density spike, provided a clear, multi-instrument confirmation of the crossing. Each of these instruments works together like sensors in a living organism. The PWS hears the plasma, the MAG feels the magnetic field, the CRS counts the energetic particles, and the LECP tracks the solar wind's dying breath. Together, they paint a complete picture of an environment that no one had ever directly observed before. And all of it comes from technology designed in an era when most scientists believed the spacecraft would never reach beyond Saturn. What makes these measurements even more remarkable is the challenge of communication. Voyager's radio transmitter sends data back to Earth using a signal so faint that by the time it reaches us, its power has dropped to about 1/20th of a billionth of a watt, weaker than the background noise of the universe. It takes enormous antennas on Earth, some spanning 70 meters, to catch and amplify this whisper of information. The signal takes more than 22 hours to travel one way, so every command sent to Voyager and every bit of data received must be timed and interpreted with painstaking care. Despite those challenges, the data that does come through remains astonishingly precise. For instance, the plasma wave subsystem doesn't record sound, but when converted to audio frequencies, its signals can be heard as eerie, high-pitched tones, literal songs of space. Those ghostly sounds represent the oscillations of electrons around Voyager, carrying the physical properties of the environment encoded within them.
Listening to those tones, scientists can trace the spacecraft's journey from the turbulent, sunlit regions of the heliosheath to the cold, compressed plasma beyond the heliopause. Voyager's instruments are now decades beyond their expected lifespan, running on a dwindling supply of nuclear power from their radioisotope thermoelectric generators, RTGs. To conserve energy, engineers have slowly been shutting down non-essential systems, heaters, cameras, and other instruments, to keep the plasma and cosmic ray detectors running. Despite this, the data Voyager sends continues to refine our understanding of how the Sun's influence fades into the galaxy. Every reading, every pulse of plasma, every magnetic fluctuation tells us something new about the invisible forces that define our cosmic neighborhood. So, when scientists say Voyager detected a 50,000-degree plasma wall, it's not because it photographed a glowing structure or directly measured heat. It's because those ancient, still-functioning instruments, the plasma sensors, the magnetometers, the cosmic ray detectors, together decoded the invisible physics of a place where no human-made object had ever been. Through those instruments, Voyager became our eyes and ears at the galaxy's doorstep, turning raw data into a story of turbulence, heat, and cosmic transformation. When Voyager 1 and 2 were launched in the late 1970s, the idea that they might one day reach the edge of the solar system was an exciting but distant dream. Scientists at the time had only rough theoretical models of what that frontier might look like. They envisioned a simple transition, a gradual fading of the Sun's influence until it blended smoothly into the calm, thin expanse of interstellar space. The prevailing expectation was that the solar wind, the stream of charged particles flowing outward from the Sun, would eventually slow down and disperse quietly as it met the interstellar medium. Beyond that, they imagined Voyager would find a relatively stable, cold, and placid region, a kind of galactic stillness after the turbulent energy of the heliosphere. The classical picture of the heliosphere painted it as a bubble of hot plasma carved into the interstellar gas, with a few distinct layers. Closest to the Sun was the supersonic solar wind, racing outward until it hit the termination shock, where it would slow to subsonic speeds. Beyond that was the heliosheath, a region of slower, denser, and cooler plasma, where the Sun's wind mixed with the galactic medium. Finally, scientists believed Voyager would pass through a thin boundary, the heliopause, marking the outer edge of the Sun's influence. Beyond that, the expectation was simple. The density of solar particles would drop sharply, the interstellar medium would dominate, and everything would become relatively calm. In short, many expected the solar system to end quietly. The edge would be like crossing from a warm, sunlit sea into the dark calm of a larger ocean, a place of gentle transition, not chaos. But when Voyager reached this boundary, the data painted a picture that defied almost every assumption. Instead of a smooth gradient, Voyager encountered a violent, turbulent frontier. As it approached the heliopause, the spacecraft detected massive fluctuations in particle density, with charged particles from both the solar wind and the interstellar medium colliding and compressing against one another. Scientists had predicted a drop in temperature. Instead, Voyager found a sharp rise, with plasma temperatures reaching about 50,000 degrees Fahrenheit, far hotter than expected. This was not a gentle blending of forces, but a collision zone, a cosmic shock front where the Sun's outflow slammed into the galaxy's counterpressure, generating intense heat and magnetic tension. Even more surprising was what Voyager didn't find. The direction of the magnetic field didn't change dramatically as expected. Theoretical models suggested that once the spacecraft crossed the heliopause, the solar magnetic field would give way to the interstellar magnetic field, pointing in a completely different direction. But Voyager's magnetometer recorded almost the same orientation on both sides of the boundary. This puzzled scientists deeply. It hinted that the magnetic fields might be interwoven or connected, forming a tangled transitional layer rather than a clean dividing line. The discovery forced researchers to rethink how the Sun's magnetic influence fades and interacts with the galaxy's magnetic environment. Another major surprise was the density of plasma beyond the heliopause. Models had predicted that the interstellar medium would be sparse, perhaps 0.002 particles per cubic centimeter. Yet Voyager's plasma wave system detected densities more than 40 times higher than that inside the heliosphere. It wasn't a vacuum at all. It was a dense, compressed layer of charged material. This indicated that the heliosphere doesn't simply end. It's squeezed by the galactic medium, like a balloon being pressed on all sides by the surrounding air. The result is a hot, dense shell, the very wall that Voyager stumbled into. The spacecraft also recorded shock waves from solar eruptions that traveled all the way from the Sun to the edge of the heliosphere, taking about a year to arrive. When these shock waves hit the boundary, they created oscillations in the plasma, like ripples on a drumhead. Scientists hadn't expected solar activity to have such a powerful influence so far from home. Yet Voyager's instruments proved that the Sun's heartbeat can still be felt billions of miles away, shaping the very frontier of our cosmic neighborhood. One of the most striking differences between prediction and reality involved cosmic rays. Before Voyager reached the heliopause, models suggested that galactic cosmic rays would gradually increase as the Sun's shielding weakened. But instead, Voyager recorded a sudden dramatic spike in cosmic ray intensity right at the boundary. It was as if the heliopause acted like a membrane, holding back most cosmic rays until they finally broke through all at once. This discovery showed that the heliosphere functions as a far more effective radiation shield than previously believed, one that protects the planets from much of the galaxy's high-energy bombardment. In the years since Voyager's crossing, scientists have revised nearly every model of the solar system's edge. What was once thought to be a smooth, spherical bubble now appears to be lumpy, uneven, and reactive, shaped by both solar activity and the galactic environment. The heliosphere may even have a tail, a long stream of plasma trailing behind the Sun as it moves through the galaxy. Voyager 2's later data confirmed that this boundary is not the same everywhere. The heliopause is closer in some directions, farther in others, and constantly shifting, like the surface of a living, breathing organism. In the end, what Voyager found was not the quiet boundary of an isolated system, but the roaring frontier of two colliding worlds. The Sun's magnetic empire, clashing with the galaxy's interstellar sea. It showed us that the solar system doesn't simply end. It fights its way into the galaxy, its last breath heating and brightening in defiance before fading into the cold beyond. Voyager's findings didn't just correct our maps of the solar system's edge, they transformed them. The old picture of a calm, static border gave way to a vision of an energetic, dynamic interface, one that responds to solar storms, fluctuates with cosmic pressure, and crackles with heat and magnetism. It's a place of constant tension and transformation, where the rules of both solar and galactic physics intertwine. For the scientists who had expected serenity, the reality was far more thrilling and far more mysterious. The solar system's edge, it turns out, isn't a quiet frontier. It's a battlefield of forces, a living threshold between the world we know and the galaxy beyond. And Voyager, against all odds, was there to witness it firsthand. The revelation that the plasma at the edge of our solar system reaches nearly 50,000 degrees Fahrenheit left scientists stunned. By every expectation, the temperature should have dropped as the solar wind weakened, cooled, and merged with the thin gas of interstellar space. Instead, Voyager recorded a spike in heat and density, showing that something dramatic was happening where the Sun's influence meets the galaxy's. The simplest explanation is compression.
When particles are squeezed together, their energy rises. As the sun's solar wind races outward, it eventually collides with the slow, dense interstellar medium. The two forces can't pass through each other, so they build pressure, creating a shock zone where motion energy is converted into heat. Voyager, passing through this turbulent layer, detected plasma vibrating with enormous energy, proof that it had entered a region under intense compression. But compression alone doesn't explain everything. Many scientists now think magnetic fields play a key role in heating the plasma. The galaxy's magnetic field wraps around the heliosphere like a net, while the sun's magnetic field spirals outward through the solar wind. Where these fields meet, they twist, reconnect, and snap apart, a process called magnetic reconnection. Each reconnection releases bursts of energy, accelerating nearby charged particles and heating them to extreme temperatures. This may be happening continuously at the heliopause, turning the boundary into a kind of invisible furnace fueled by magnetic tension. Another contributor could be solar shock waves, huge pulses of plasma and magnetic energy ejected from the sun during powerful eruptions. These waves travel outward through the heliosphere for over a year before finally slamming into the boundary region. When they arrive, they crash into the dense plasma beyond the heliopause, producing oscillations and temporary spikes in temperature. Voyager has actually heard these impacts through its plasma wave instrument, eerie radio-like vibrations echoing through the void. Each impact re-energizes the outer plasma, preventing it from cooling down completely. There's also the role of charge exchange, a subtle but powerful interaction. When fast-moving solar ions collide with slow neutral atoms from interstellar space, they can swap electrons, creating newly charged particles that carry fresh energy. This constant exchange stirs and heats the plasma, keeping it active and unstable. Over billions of miles, these micro-interactions accumulate into significant energy gains, maintaining the plasma's surprisingly high temperature. Some scientists point to turbulence as another heat source. As the solar wind slows and mixes with the interstellar medium, chaotic eddies of plasma form, cascading energy down to smaller and smaller scales. That turbulence transfers motion into heat without requiring frequent collisions between particles, a process similar to how air can warm up as it flows through a jet engine. In the vast emptiness of space, this microscopic turbulence becomes one of the few ways energy can be distributed efficiently. Together, these effects, compression, magnetic reconnection, charge exchange, solar shock waves, and turbulence, form a complex system that keeps the plasma hotter than anyone expected. Rather than a quiet edge, the heliopause is a living, reactive frontier, constantly reshaped by the push and pull between the sun's outflow and the galaxy's incoming pressure. This new understanding has broader implications too. Every star produces its own heliosphere or astrosphere, and if our sun's boundary is this energetic, others may be as well. It suggests that the outer edges of stellar systems across the galaxy are far more active than once believed, glowing not with light, but with hidden heat and magnetism. Voyager's discovery revealed that the sun's power doesn't fade into nothingness, it transforms. The solar wind's final journey ends not in silence, but in resistance, a blazing boundary where motion becomes energy and energy becomes heat, before merging with the vast, cold flow of the galaxy beyond. The best way to visualize what Voyager discovered at the edge of the solar system is to imagine a bow shock, the kind of pressure wave that forms when an object moves through a fluid faster than the surrounding medium can disperse the energy. It's the same principle that creates the sonic boom of a jet plane or the V-shaped ripple of a ship cutting through water. In space, however, there's no sound, no ocean, and no air. But there is plasma, magnetic pressure, and motion on a galactic scale. The sun, traveling through the Milky Way at roughly 450,000 miles per hour, acts just like that ship, pushing against the thin interstellar gas that fills the galaxy. The result is a massive, invisible shock front at the outer boundary of the heliosphere, the heliopause, where the solar wind slams into the interstellar medium and builds up pressure. For decades, scientists theorized that such a bow shock must exist, but they had no way to confirm it. When Voyager reached the heliopause, the data suggested that while the shockwave might not be as sharp or dense as a jet's sonic boom, the same physics applies. The sun's outflow of charged particles, traveling at supersonic speeds relative to the local interstellar gas, slows and compresses dramatically as it encounters resistance. The particles pile up, magnetic fields bend and intensify, and plasma density spikes, creating a region that behaves like a cosmic shockwave, rippling with energy and heat. Voyager's instruments, particularly its plasma wave detector, recorded evidence of these compressions in the form of oscillations, echoes of invisible shock fronts rolling across billions of miles. This bow shock analogy helps make sense of the extreme heating and particle buildup Voyager observed. Just as air molecules are compressed and heated at the nose of a supersonic jet, the solar wind's charged particles are squeezed and energized as they collide with the interstellar medium. The result is a turbulent interface where the sun's energy is abruptly converted into thermal motion, the source of the 50,000-degree plasma wall. Scientists now think the heliopause might act as a blunt obstacle in the flow of galactic plasma, deflecting some material while absorbing the pressure of the rest. This would explain why the region is both hotter and denser than expected, and why Voyager measured such sudden jumps in plasma energy. However, the shock at the heliopause is not perfectly steady or symmetric. Unlike a jet or ship, which moves through a relatively uniform medium, the sun's surrounding environment is patchy and magnetically uneven. The interstellar gas itself flows around us, carrying its own weak magnetic field, and its density varies from one region to another. This means the heliopause isn't a clean, smooth surface, but a constantly shifting frontier, rippling like a flag in a slow, cosmic wind. Voyager's readings show fluctuations in pressure and temperature that rise and fall as the solar wind changes, suggesting that the bow shock breathes, expanding during solar storms and relaxing during quiet periods. In this sense, the heliopause might be more like the wake of a ship than the sharp nose of an aircraft. The sun's motion through the galaxy stretches the heliosphere into a teardrop shape with a compressed nose at the front and a long trailing heliotail streaming behind. At the leading edge, the direction we're moving through the Milky Way, the solar wind piles up against the galactic flow, forming the shock-like barrier Voyager encountered. But behind us, the sun leaves a trail of magnetized plasma that stretches for billions of miles, gradually merging with the interstellar medium. Voyager 2, traveling in a different direction from Voyager 1, has begun to map the shape of this region, confirming that it's asymmetrical and dynamic. What's truly fascinating is how these bow shock-like interactions reveal that even the emptiest regions of space are far from still. The heliopause is a place of constant tension, where motion, magnetism, and plasma physics converge in a delicate balance. It behaves almost like a giant, slow-motion shockwave, one that defines the very limits of our solar system's protective shell. In the same way that a ship's bow wave separates the calm water behind it from the rough, open ocean ahead, the heliopause separates the solar system's relatively quiet interior from the vast, unpredictable expanse of interstellar space. Voyager's detection of this phenomenon was monumental because it proved that our solar system doesn't simply float passively through the galaxy. Instead, it interacts dynamically with its environment, ploughing through the galactic medium and shaping it as it moves. The Sun's outflow of plasma carves a cavity in the interstellar gas, while the interstellar gas pushes back, compressing and heating the outer layers in a constant struggle for balance. The result is a frontier that is neither solar nor galactic, but something in between, a liminal zone of pressure, motion, and heat. This shockwave analogy helps bridge human intuition with cosmic reality. We can't see or hear what happens out there, but Voyager's instruments have essentially felt the resistance of the galaxy pushing against the solar wind. That faint resistance, recorded across billions of miles, tells us that our solar system sails through the Milky Way not as a silent observer, but as an active participant, shaping and being shaped by the very fabric of the interstellar medium. And as Voyager continues its journey beyond that bow-shaped frontier, it carries us across the solar system's last ripple, from the turbulent surf of the Sun's domain into the calm, dark waters of interstellar space itself. Voyager's discovery of the 50,000-degree plasma wall wasn't just a startling revelation about a distant region of space. It was a profound insight into how our solar system interacts with the galaxy around it. Until this finding, we thought of the Sun's domain as largely self-contained, its influence fading into the void without much resistance. But what Voyager revealed changed that perspective entirely. It showed that our solar system doesn't exist in isolation. It's part of a larger, dynamic system where the Sun and the Milky Way are in constant dialogue, a cosmic tug-of-war of matter, magnetism, and motion. This discovery matters because it redefines how we understand the boundaries of our home in the universe. The heliopause, the invisible barrier between solar and interstellar space, is not a static shell, but a living frontier where the solar wind and the galaxy's interstellar medium meet, collide, and reshape each other. By studying this interaction, scientists can see, in real time, how stellar systems carve out bubbles in the galactic medium and how those bubbles respond to external pressures. Every star, including our own, exists within such a bubble, an astrosphere, and the behavior of our heliosphere gives us a model for understanding these structures across the galaxy. One of the most critical implications of Voyager's data is what it tells us about cosmic radiation and shielding. The heliosphere acts as a natural barrier that protects the solar system from the most energetic cosmic rays, particles accelerated by supernova explosions and galactic magnetic fields. These cosmic rays can be incredibly destructive, capable of damaging DNA, disrupting electronics, and altering planetary atmospheres. By mapping how the heliosphere filters and deflects these rays, Voyager's measurements help us understand how vital this magnetic shield is for sustaining life on Earth. It's a reminder that even though we live 93 million miles from the Sun, our survival depends on how effectively the Sun's influence extends into space. Understanding the interaction between the solar wind and the interstellar medium also deepens our grasp of galactic ecology, the complex exchange of energy and matter that keeps the Milky Way evolving. The solar wind carries charged particles, magnetic fields, and plasma far into the galaxy, while the interstellar medium brings back dust, neutral gas, and radiation. The boundary where they meet is like a membrane, allowing certain materials and energies to pass through while reflecting others. Voyager's readings give us the first direct observations of how this cosmic weather system operates at the edge of our own solar bubble. These findings also have far-reaching implications for understanding the Sun's history and the future of our solar system. As the Sun orbits the center of the Milky Way every 230 million years, it passes through regions of varying interstellar density. In denser regions, the heliosphere could shrink, bringing the boundary closer to the planets and exposing them to more cosmic radiation. In thinner regions, the bubble expands, offering greater protection. Voyager's data allows scientists to model how these changes might have influenced Earth's climate and biology over geological time, and how they could affect us in the distant future. The significance extends even further into astrophysics and planetary science. Before Voyager, no spacecraft had ever directly measured the properties of interstellar plasma. Everything we knew about the medium between stars came from remote sensing, telescopes, and spectral analysis. But now, with Voyager's readings, we have in situ data, real numbers on particle density, magnetic strength, and plasma frequency. This has given astronomers an entirely new calibration point for studying how stars, nebulae, and galactic fields interact. It's as though we've finally dipped a thermometer into the space between stars, and what it's shown us is far more energetic and complex than we ever imagined. On a more philosophical level, Voyager's discovery touches something deeper: the idea that the solar system is not a closed, solitary island, but an open system immersed in the galaxy's vast environment. Our Sun breathes plasma outward, and the galaxy breathes plasma inward, and where the two meet is where the story of connection begins. It's a humbling reminder that the boundaries we draw between our solar system and the rest of the cosmos are not walls, but relationships. The heliopause is not a limit. It's a handshake between the Sun and the stars. This discovery also reframes how we think about space exploration. Every mission beyond Earth's orbit, from Mercury probes to Mars rovers to the Voyagers themselves, has been an exploration within the Sun's protective bubble. Now, with Voyager in interstellar space, humanity has finally crossed that threshold. The data it sends back helps us understand not just what's out there, but also how future explorers, robotic or human, might fare when we one day venture beyond the Sun's reach. By understanding the nature of this plasma wall, we can design better instruments and shielding for spacecraft that will follow Voyager into the interstellar dark. Ultimately, this discovery underscores a truth that feels both scientific and poetic. Our solar system is not isolated. It is alive within the galaxy. It pulses, flexes, and changes as it interacts with the wider Milky Way. The heat Voyager found is not just physical, it's symbolic of that connection. It's the glow of our Sun's boundary pushing back against the galaxy's embrace, an incandescent marker of where home ends and the cosmos begins. Voyager's crossing of this fiery frontier didn't just expand our scientific knowledge, it expanded our sense of belonging in the universe. It reminded us that even at 14 billion miles away, the Sun's influence endures, that our small solar bubble is part of something immeasurably larger, and that the very forces that protect us also connect us to the stars themselves. Perhaps one of the most astonishing parts of this entire story isn't just what Voyager has discovered, but that it's still able to discover anything at all. These twin spacecraft, Voyager 1 and Voyager 2, were launched more than 48 years ago, in 1977, using technology that predates the modern computer age. They were built when engineers still relied on slide rules, magnetic tape, and hand-drawn schematics. Yet here we are, nearly half a century later, still receiving precious data from machines now over 14 billion miles away. Machines that have outlived every expectation and remain humanity's most distant and enduring explorers. Voyager's endurance is nothing short of miraculous. Each probe carries a small radioisotope thermoelectric generator, RTG, a nuclear power source that converts heat from the radioactive decay of plutonium-238 into electricity. When they launched, those generators produced about 470 watts of power, roughly equivalent to a household light bulb. Over time, that power has been steadily fading
as the plutonium decays. Today, the spacecraft operate on less than half that amount, yet they continue to run a small handful of instruments, transmit data, and respond to commands from Earth. To conserve power, NASA's engineers have spent decades strategically shutting down systems, heaters, cameras, and non-essential instruments, keeping only the most crucial sensors alive, those that study plasma, magnetic fields, and cosmic rays. What's even more remarkable is that these spacecraft are running on computers less powerful than a digital watch. Each Voyager's onboard computer has about 69 kilobytes of memory, not gigabytes, not megabytes, but kilobytes. That's less than the size of a single small image file. The programming that controls them was written in the language of the 1970s, stored on old magnetic tape, and transmitted through a system of backup circuits designed for redundancy, not longevity. Yet somehow, through the dedication of engineers across generations, these ancient computers still process data, perform course corrections, and send transmissions home with astonishing precision. And what those transmissions endure to reach us borders on the unbelievable. Voyager's signal travels for more than 22 hours across 14 billion miles of space, weakening to a whisper, about 1/20th of a billionth of a watt by the time it reaches Earth. Capturing that signal requires NASA's Deep Space Network, a collection of massive radio antennas spread across California, Spain, and Australia. These dishes, some up to 70 meters wide, listen day and night for Voyager's faint heartbeat, amplifying the signal billions of times over to extract mere bits of data, information about magnetic fields, plasma densities, and cosmic radiation that is priceless to science. Every communication with Voyager is a slow and deliberate process. When NASA sends a command, it takes nearly a full day for the instruction to arrive, and another day for Voyager's response to come back. That means even the simplest command, turning an instrument on or off, takes nearly 2 days to verify. It's an exercise in patience and precision, one that embodies the perseverance of human curiosity. The scientists and engineers managing the mission often say it feels like talking to an old friend through a time machine. That description feels fitting. Voyager is, in every sense, a time capsule from another era, not just because of the golden record it carries, but because the spacecraft themselves are relics of human craftsmanship and faith in exploration. The golden records, made of gold-plated copper, contain the sounds and images of Earth, greetings in 55 languages, music from Bach to Chuck Berry, and the murmur of waves and wind. They were placed there not just as a message to alien civilizations, but as a message to time itself, a statement that humanity once dared to reach beyond its cradle. Now, those records are traveling in interstellar space, destined to drift among the stars for billions of years, long after the Earth, the Sun, and all of us are gone. But what makes Voyager's endurance even more inspiring is the human story behind it, the continuous, decades-long effort of the small team at NASA's Jet Propulsion Laboratory who have kept these spacecraft alive. Many of the engineers who built Voyager have long since retired or passed away. Today's mission team includes scientists who weren't even born when the probes were launched. They inherit handwritten notes, decades-old software, and hardware so ancient that spare parts must be scavenged from museums and storage facilities. And yet, they continue to troubleshoot and problem-solve, sometimes rewriting decades-old code, sometimes rerouting power through systems designed in a different century. Every few years, NASA faces the question, should the Voyagers keep going? And every time, the answer is yes. The data they return about the heliopause, the plasma wall, and the interstellar medium is utterly unique. No other spacecraft in history has reached this region, and none will for many decades to come. Voyager is still doing frontier science,
measuring the invisible environment that defines the edge of our solar system. Even with its fading instruments and dwindling power, it continues to send back data that reshapes our understanding of the universe. As of now, the projections suggest Voyager's power supply will last until about 2030 to 2035. After that, the RTGs will no longer produce enough electricity to power its instruments or radio transmitter. When that day comes, Voyager will finally go silent, its voice fading into the cosmic background it once studied. But even then, it won't truly die. The spacecraft will keep coasting through interstellar space, moving at about 38,000 miles per hour, drifting silently toward the stars. In 40,000 years, Voyager 1 will pass within 1.6 light-years of another star, Gliese 445, in the constellation Camelopardalis. Long after humanity is gone, that little probe will still be carrying our story, still bearing the message that, once upon a time, a small species from a pale blue planet reached out to touch the stars. Voyager's endurance isn't just mechanical, it's symbolic. It's proof that human curiosity can outlast generations, that a spark of exploration can burn for half a century across billions of miles. Its continuing voice, whispering through the cosmic dark, reminds us that even when our machines are old and their power is fading, our desire to know never dims. Voyager's crossing into interstellar space wasn't just a boundary event. It was a first look into an entirely new kind of environment, one that had existed only in theory for generations of scientists. Until Voyager 1 broke through the heliopause, humanity had never directly sampled the interstellar medium, the vast expanse between the stars. Everything we knew about that region came from indirect measurements, light spectra, radio emissions, and computer models. But those were guesses, not direct encounters. When Voyager sent back its first readings from beyond the Sun's protective bubble, it provided the first physical evidence of what it's truly like out there. The density, the heat, the pressure, and even the sound of interstellar space itself. That's what makes this discovery so transformative. Voyager's instruments, even after decades of wear and diminishing power, gave scientists their first preview of the true interstellar environment, a place that is both harsher and more dynamic than anyone had expected. Instead of the cold, empty void scientists imagined, the data revealed a surprisingly dense and energetic region, filled with plasma vibrations, charged particles, and subtle magnetic disturbances. The interstellar medium, Voyager showed us, is not silent. It hums with activity. The spacecraft's plasma wave subsystem has literally heard the oscillations of interstellar plasma, converting them into faint ghostly tones, the music of space itself. Those vibrations confirmed that Voyager had entered a region where the Sun's influence no longer dominates, where the plasma density is roughly 0.05 particles per cubic centimeter, about 40 times denser than inside the heliosphere. This environment is extreme, but it's also revealing. For decades, scientists wondered how the galactic environment might affect planetary systems like our own, how cosmic rays, interstellar dust, and magnetic fields interact with the boundaries of stellar bubbles. Now, thanks to Voyager, we know that these boundaries are complex, multi-layered zones where the forces of stars and the galaxy balance in intricate ways. The discovery of the plasma wall, a region of compressed, superheated particles, was a stunning example of that complexity. It showed that the edges of a solar system are not calm or inert. They are alive with energy, constantly shaped by the tug-of-war between stellar winds and the galactic medium. Voyager's readings also provided crucial information about cosmic rays, those high-energy particles that stream in from all directions of the galaxy. Inside the heliosphere, the Sun's magnetic field deflects many of them, but beyond the heliopause, that shielding vanishes.
Voyager's cosmic ray detector recorded a sudden, dramatic increase in their intensity, the first real measure of the raw galactic environment our solar system is sailing through. Understanding that radiation field is essential not just for astronomy, but for the future of interstellar travel. It gives us a sense of what spacecraft, or one day humans, would face once they leave the sun's protection. Equally significant are the magnetic field measurements. Voyager's magnetometer showed that the interstellar magnetic field is both stronger and more structured than previously thought. Instead of encountering a field that ran in a completely different direction from the solar field, Voyager found one that seemed aligned or tangled with it. This suggests that the sun's magnetic influence extends farther than expected, that even beyond the heliopause, remnants of the solar field interact with the galaxy's magnetic fabric. This overlapping of fields creates a region of turbulence and complexity that might be common around other stars too. It means the heliosphere, and by extension, every stellar bubble, isn't just a clean edge, but a transitional zone, a magnetic bridge between star and galaxy. These findings have become the foundation for the next era of interstellar exploration. Voyager has effectively served as a pathfinder, giving us the first data points we'll need to design missions capable of venturing deeper into the galaxy. Future spacecraft, like the proposed interstellar probe currently being studied by NASA, will use Voyager's discoveries to determine how to measure, shield, and navigate through the interstellar medium. They'll know what to expect: the density of plasma, the strength of magnetic fields, and the temperature of the charged particles that fill the space between stars. Without Voyager's endurance and discoveries, those missions would be flying blind. On a more philosophical level, Voyager's passage into interstellar space marks a turning point for humanity. For the first time, one of our creations has entered a region that belongs not to the Sun, but to the Milky Way itself. Voyager's data gives us more than science. It gives us perspective. It reminds us that the Sun, the planets, and even the heliosphere are not isolated islands, but parts of a much larger ecosystem, a galactic ocean teeming with energy and motion. The plasma wall, the magnetic compression, the constant hum of cosmic rays. These are the currents and tides of that ocean, and for the first time, we are beginning to feel them directly. Voyager's entry into this realm has also helped scientists begin to map the transition between local and galactic space. We are learning, in quantitative terms, how much pressure the interstellar medium exerts on the heliosphere, how the Sun's outflow changes as it leaves the solar domain, and how the cosmic environment affects planetary systems like ours. It's a small but vital step toward understanding how the galaxy behaves on a grand scale, and how our tiny solar system fits into that vast puzzle. In a way, Voyager's crossing of the heliopause is humanity's first reconnaissance mission into the galaxy. Its sensors, still sending data across 14 billion miles of emptiness, are giving us a real-time weather report from interstellar space. Every reading tells us how the Sun interacts with its surroundings, how the boundary breathes, shifts, and responds to the storms of both the Sun and the Milky Way. We are, for the first time, watching our solar system not as the center of everything, but as one small bubble moving through the greater currents of the cosmos. That's why this discovery matters so profoundly. Voyager didn't just leave the solar system, it connected it, linked our small corner of space to the vast galactic environment that sustains it. The data it sends isn't just a record of physical measurements. It's a glimpse into the architecture of the galaxy itself, the invisible forces that bind stars, planets, and interstellar matter together. Voyager's crossing was not the end of exploration. It was the beginning of interstellar discovery, the first whisper from the true universe beyond our Sun. Voyager's journey into interstellar space is not just a triumph of endurance, it's a blueprint for the future.
Every bit of data that the spacecraft has sent back, every reading of plasma density, magnetic field, or cosmic ray intensity has become a foundation upon which future missions will be built. Before Voyager, the outer reaches of the solar system and the space beyond were matters of theory and speculation. Now they are charted territory, albeit faintly and imperfectly, with real measurements that show what the conditions are like beyond the Sun's protective bubble. These discoveries have already started shaping the next generation of interstellar probes, spacecraft designed not just to reach the edge, but to go far beyond it. The challenges of interstellar exploration are immense. Outside the heliosphere, the Sun's light is so faint that solar panels become useless. The temperatures drop to near absolute zero. Cosmic rays and high-energy particles constantly bombard anything that ventures there. Communication takes nearly a day in each direction, and power must last for decades. Voyager's success in overcoming these challenges provides an invaluable guide for engineers and scientists designing new missions. One of the most promising concepts inspired by Voyager's data is NASA's proposed interstellar probe, currently under study at the Johns Hopkins Applied Physics Laboratory. This spacecraft would be built using everything we've learned from Voyager, but with modern technology and greater speed. The mission's goal would be to travel 3 times farther than Voyager has, reaching up to 1,000 astronomical units, nearly 100 billion miles, from the Sun over the course of 50 years. Thanks to Voyager's measurements, scientists now know what to expect in terms of plasma density, radiation levels, and magnetic turbulence. Information that is essential for designing sensors capable of surviving and performing in such a harsh, low-energy environment. For example, Voyager's discovery of the dense plasma layer beyond the heliopause has taught mission planners that future instruments will need greater sensitivity and noise reduction to detect subtle fluctuations in that environment. New probes might carry advanced plasma analyzers with wider dynamic ranges, capable of recording both the low-energy solar wind and the hotter, more energetic interstellar particles that Voyager's aging instruments could only partially measure. Similarly, the discovery that the interstellar magnetic field interacts intricately with the Sun's field means that next-generation spacecraft will need more precise magnetometers, instruments that can detect extremely faint shifts in magnetic orientation across billions of miles. Voyager also revealed that the heliopause is not a simple, static boundary. It fluctuates with the Sun's 11-year solar cycle and responds to large solar storms. This finding is crucial for future missions, as it means spacecraft crossing that boundary must be able to adapt to changing conditions, perhaps with real-time onboard data analysis and autonomous decision-making. Where Voyager sent data home for slow interpretation, new probes could use artificial intelligence to respond instantly to variations in plasma pressure, optimizing their observations while minimizing risk. The lessons extend beyond instrumentation. Voyager's power system, the radioisotope thermoelectric generator, RTG, has proven the durability of nuclear energy in deep space. Future missions will likely use next-generation RTGs with higher efficiency and longer lifespans. Engineers are also considering miniaturized nuclear reactors or alternative radioisotopes that could provide steady power for a century or more. Without Voyager's performance as proof, these ideas might never have advanced beyond speculation. Now, we know that nuclear power is not only viable, but essential for interstellar exploration. Even Voyager's communication systems have informed the future. Its faint, 23-watt radio signal, weaker than the power of a refrigerator light bulb, still reaches Earth because of the immense sensitivity of NASA's deep space network. Future probes, though, will travel so far that communication delays could stretch to multiple days. Thanks to Voyager, mission designers know that spacecraft must carry smarter data compression systems, autonomous diagnostics, and possibly optical communication, laser-based transmitters, to handle the distances efficiently. In short, Voyager has taught us not just about the cosmos, but about how to talk across it. Its data is also reshaping how scientists model other stars' astrospheres, the analogues of our heliosphere that surround stars throughout the galaxy. The plasma and magnetic conditions Voyager measured give astrophysicists the first hard numbers to test theories about how these bubbles interact, overlap, and protect planetary systems from cosmic radiation. That, in turn, informs the search for habitable worlds. By understanding how stellar winds shape their environments, we can better predict which exoplanets might enjoy the same kind of protection Earth receives from our Sun's heliosphere. Moreover, future missions inspired by Voyager might not just study interstellar space, they might navigate it. By analyzing Voyager's findings on interstellar plasma, engineers can design spacecraft that use plasma propulsion systems capable of interacting with the environment around them, drawing minimal thrust from the particles between the stars. Though still theoretical, such propulsion could one day allow continuous acceleration through the interstellar medium, a dream that begins with data from Voyager's 1970s-era instruments. The spacecraft's endurance also set a benchmark for how long machines can last in the cold, radiation-rich void of deep space. Its reliability has informed the design of all long-duration missions since, from New Horizons to future probes that may reach the Oort cloud or beyond. Every calibration, every thermal shield, every redundant circuit designed for a century-long mission owes something to Voyager's example. In essence, Voyager's findings have done more than just describe interstellar space. They have opened it. They've given humanity its first navigational chart for the great beyond, the first understanding of what a spacecraft might face when it leaves the Sun's domain. The next generation of explorers, robotic or otherwise, will travel into that darkness armed with knowledge Voyager earned through decades of silence, patience, and endurance. So when the first purpose-built interstellar probe finally launches, decades from now, it will not be venturing into the unknown blindly. It will be following a path lit by Voyager's faint signal, guided by data from a craft built with 1970s technology and 20th century dreams. Voyager has shown us not just how to reach the edge of the Sun's influence, but how to prepare for what lies beyond it. It's almost beyond comprehension that something built by human hands, with technology older than most people alive today, is now beyond the Sun's protective bubble, floating alone in the interstellar dark. Voyager 1 is more than 14 billion miles from home, yet it's still speaking to us, still sending faint whispers of data across a sea so vast that each transmission takes nearly a full day to arrive. It's a fragile emissary of Earth, running on fading nuclear heat, drifting through a realm colder and lonelier than anything we can imagine. And yet, it endures. When you think about it, Voyager isn't just a spacecraft. It's a symbol of what humanity is capable of at its best: curiosity, persistence, and the desire to understand. Long after its designers retired, long after the world it launched from has changed in ways they couldn't imagine, their creation continues to work exactly as intended. It's the purest form of legacy, not written in stone or steel, but in motion and purpose, sailing through eternity. And somewhere out there, in that endless darkness, Voyager carries the golden record, our message in a bottle to the cosmos. Greetings in 55 languages, the sound of rain, a mother's kiss, a baby's cry, the laughter of a species reaching for the stars. Voyager is not just a machine, it's a monument to hope, proof that even a small, fragile civilization dared to touch infinity. As Voyager drifts ever deeper into interstellar space,
It is moving into a realm no spacecraft and no human has ever experienced. What lies ahead is both mysterious and unpredictable. The spacecraft is now in a region where the sun's influence is almost gone, and the galaxy itself begins to take over. Scientists believe that Voyager will continue to detect gradual changes in the density and temperature of the plasma around it, revealing how the interstellar medium varies across different regions of the Milky Way. In the coming years, Voyager may encounter shifts in magnetic fields, perhaps even passing through areas where the galactic magnetic field becomes stronger or changes direction entirely. These variations could help scientists understand how the galaxy's magnetic web is structured, how it weaves through interstellar space, shaping the movement of cosmic rays and influencing the birth of new stars. The spacecraft might also pass through interstellar clouds, denser pockets of gas and dust that drift through the galaxy. If it enters one, the plasma density around it could increase dramatically, giving us an even deeper look into how the local interstellar environment behaves. Some scientists speculate that Voyager could detect new kinds of particles or cosmic phenomena we've never directly observed. Beyond the heliosphere, radiation levels are higher, and interstellar plasma behaves differently, perhaps revealing unknown particle interactions or subtle energy fields that our models haven't predicted. Each bit of data Voyager sends home could be a clue to something entirely new, a surprise waiting in the darkness. There's also the tantalizing possibility that Voyager will continue to experience shockwaves from the sun for years to come. Even now, powerful solar eruptions travel outward at unimaginable distances, taking over a year to reach Voyager's location. These faint tremors from the sun, our star's last whispers, will continue to ripple through interstellar space, and Voyager may be there to record them, documenting how solar energy echoes across the galaxy's edge. Yet the most haunting reality is that one day the signal will stop. The power will fade, the instruments will fall silent, and Voyager will finally become a ghost ship, coasting silently among the stars. But even then, its journey won't be over. It will keep traveling, through the galaxy's magnetic currents, past distant clouds and unseen fields, carrying its golden record, and with it, the story of a species that once looked to the night sky and dared to wonder. Voyager's journey is more than a scientific mission. It's a human epic written across the stars. In less than a century, we went from looking up at the night sky to sending a machine so far that the sun is now just another star in its sky. The discovery of the 50,000-degree plasma wall at the solar system's edge stands as one of the most extraordinary milestones in that odyssey. A reminder that even after decades of exploration, the universe can still surprise us. Voyager revealed that the boundary of our solar system isn't a quiet fade into the void, but a vibrant frontier of heat, energy, and motion, the very edge of the sun's heartbeat pressing against the galaxy's breath. That single discovery reshaped our understanding of how stars, planets, and galaxies interact. It showed us that our solar system is alive within a vast, interconnected cosmic web, that the sun's influence doesn't end abruptly, but dissolves into the galaxy through turbulence and fire. And Voyager, a spacecraft built when humankind had barely walked on the moon, was the one to show us. As it sails on into eternity, carrying humanity's first message to the stars, Voyager embodies the purest form of exploration. Curiosity turned into motion. Its discoveries remind us that the universe is not static or silent, but endlessly evolving, waiting to be understood. The 50,000-degree wall at the edge of our solar system isn't the end of anything. It's the beginning of everything that still lies ahead, proof that there will always be new mysteries beyond every horizon, waiting for us to find them. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect, like the video,
and subscribe to the channel for more such amazing videos.